Okay, Chemistry 3101. We said we were going to start off with question 7.19. We have our sodium methoxide, which is an unhindered base. So we have our sodium methoxide. And remember that ethoxide is an unhindered base. And so when we have an unhindered base, what does that mean? It means that the Zaitsev product is going to predominate. So we'll put here Zaitsev. Zaitsev is the major product. All right, so let's label our alpha carbon. We have two types of beta carbons here. We have the one with this blue proton on it here, like this. And then we have the ones with these black protons here. I'm going to abstract the black proton first. That's going to give us the Hofmann product. You don't have to draw a mechanism. But let's just draw a quick one. We abstract the proton, make the pi bond, lose the leaving group, which is the chloride ion. And we end up with the Hofmann product, which looks like this. So we end up, we didn't touch anything here. So we'll leave that like this, and we end up with our double bond like that. So this will be the Hofmann product, and this is going to be the minor product. All right, so when we're figuring out the, Zaitsev product, what we're going to do is we're going to draw a Newman projection the way I taught you last class. Okay, so let's do that. So let's imagine we have our eyeball here, and we're looking down this carbon-carbon bond. What are we going to see? Well, I didn't leave myself a lot of space here, but I'll try to squeeze it in here. So we have our carbon in front, and then we have the carbon in back, like this. Okay, going straight down, we have our aromatic ring, so that's our phenyl. Going off to the right-hand side, we have our proton. Over here on the left-hand side, we have our isopropyl group, like that. In the back, we have our methyl group going straight up. We have our chlorine on the same side as the proton, like that. And what else? Oops, let me fix that. We have our chlorine on the same side as the proton, and then we have a hydrogen going over here like this. So what we have to do is we have to manipulate the molecule so that this proton and the chlorine are anti-periplanar to each other. So we could either rotate the chlorine in the back. What I'm going to do is I'm going to move the proton over to this position, okay? And that's going to get them in an anti-periplanar arrangement. So let's redraw the Newman projection. So it's going to look something like this. So there's our carbon in the back. There's our carbon in the front. So the carbon in the back remains unchanged. We have our chlorine here. We have our methyl group up here. And we have our proton over here. Now we've put the proton so that it's anti-periplanar to the chlorine. We've moved the isopropyl group down at the bottom like that. And there we go. We have our methyl group, or sorry, our phenyl group going up here. And so now you can see that the proton and the chlorine are anti-periplanar. So now when I form my double bond, what do I see? I see I have the methyl group on the same side as the phenyl, right? If you don't believe me, here's the methyl group is going to be on the same side as the phenyl, like that. So now when I do the elimination, which if you want to practice the mechanism, it's just going to be this. We form the double bond, we lose the leaving group like that. What's it going to look like? It's going to look like this. So we have our aromatic ring. We have our double bond. Here's the isopropyl group. And now, like I said, the methyl group is going to be on the same side as the phenyl, like this. And so we have the proton over here. So this is the Zaitsev product. Zaitsev. And this will be the major product. All right. So I would always go through a Newman projection, and you never go wrong with a Newman projection. All right. There we go. So the next one, let's see if we can solve the next one. I'll ask you a couple of questions about the next one. So in order for the bromine, which is the only atom in here, which could be a leaving group, the only way that that can act as a leaving group is for it to be up and what? So this bromine would have to be what? An up and axial or equatorial for it to function as a leaving group for an elimination reaction to occur. Could anybody tell me it has to be up and what? Equatorial or axial? Exactly. It has to be up and axial, right? because the only way that you can have a leaving group and a proton being antiperiplanar in a cyclohexane is for both groups to be axial. So if the bromine is up and axial, that would mean that here is our alpha carbon, and we've got two types of beta protons, don't we? We have this beta proton here in blue, and then we have this beta proton here. I'll just draw it in black, okay? We have this beta proton in black. If you're wondering, why did you only draw this one with the dash? Isn't there one with a wedge? Yes, but it's not really pertinent to the problem, because the reason I drew the hydrogens on the dashes is because if the bromine is up an axial, that would mean that these hydrogens, this one is down and axial, and that would mean that this one in black is also down and axial. So there's two possible products we could get here. We could abstract either one of these beta protons. Which one's going to give us the major product? Well, if we have sodium ethoxide, okay, we can just copy and paste the information that we put up here. Sodium ethoxide is an unhindered base. It's an unhindered base, and therefore it's going to give us the Zaitsev product as the major product. So what one's going to give you the Zaitsev product? It's the one that's, where you put the double bond here, because that's going to be a tri-substituted double bond, whereas this one is going to give you a di-substituted double bond. So let's draw the product that would result from the abstraction of the blue proton. It would give you this. Okay, once you abstract that blue proton, you end up with a double bond here. And so there's your methyl group. Remember, this carbon is now sp2 hybridized, so you don't have to draw dashes and wedges. This would be the Zaitsev product, which is Zaitsev, which is the major product. And then we are also going to get this one over here, where if we abstract the proton in black, we form the double bond here, but we didn't touch this stereocenter, so we still have to draw that as a wedge. And so this is going to be the Hoffman product, Hoffman product, and this is going to be the minor product, like that. All right, there we go. So a little practice on stereoselectivity. So both of these reactions are not stereospecific, they are stereoselective. Okay, why? Because there's more than one type of beta proton in both of them. However, when you draw the Zaitsev product for the first reaction on that carbon that I had in blue before, this carbon over here, there's only one type of beta proton on that. And when you have only one type of beta proton and there's free rotation, meaning it's not in a cyclohexane, it's always best to go through a Newman projection like I taught you last class. It's pretty foolproof. All right, there we go. So let's change the subject. We've covered SN2. So far we've gone into all the details of SN2 and E2 reactions. And now we're going to turn our attention to SN1 reactions and E1. Now, when in an SN2, if the S stood for substitution and the N stood for nucleophilic, the 2 stood for second order. So what it means is that when we study SN1 and E1 reactions, it's substitution, nucleophilic, it's elimination, but 1 means first order reactions. And so if you don't remember, going back to your general chemistry 2 days, the rate law for a first order reaction is that rate is equal to the rate constant multiplied by the concentration of one thing to the power of 1, right? When we leave that out. But anyhow, in this case, it's only going to depend on the concentration of the substrate. And remember, the substrate is just a fancy word for your alkyl halide. Okay, and there's other leaving groups that we're going to see today, but or you could just say or starting material. Okay, so if we take a look at this reaction over here, if you're not awake, wake up for just a second here. I got to show you something really important. Look at this reaction. This is totally unlike anything that we've seen thus far. You're starting out not with a primary alkyl halide or a methyl, you're starting out with a tertiary alkyl halide. So that's going to be electrophilic, but it's too sterically hindered for an SN2 reaction to happen. Okay, and then if you look at the other reactant, it's just ethanol, which is a good solvent, but it's not a strong base. So that means you're not going to get an E2 reaction occurring, right? In an E2 reaction, you need a strong base. So you see what I just said is summarized right here, okay? So it turns out that this reaction, and this is kind of our conclusion of the slide, is that the formation of the substitution and elimination products, which we do get, okay, they are not, they do not follow second order kinetics, but they rather follow first order kinetics. And so it's something completely different. It's a completely new mechanism. And so if we wanted to write a rate law for this reaction, we would say rate is equal to the rate constant K multiplied by the concentration. Maybe I need a bigger bracket. By the concentration of the substrate only. Okay, that's it. That's the rate law for the whole thing. So what is this mechanism going to look like? Well, if you remember that in SN2, it was like SN together. The reaction was concerted, meaning that both the nucleophilic attack and the loss of the leaving group occurred at the same time. And what I told you last class, and if you forgot, it's totally fine, is that when it's first order, you can kind of think of it as SN1 at a time, or as E1 at a time, okay? And that just means that it's a stepwise process. So it turns out that the first step is actually just a loss of a leaving group. Now, if you're going, well, how can you have a loss of a leaving group without a nucleophilic attack occurring at the same time? Haha. The difference is in the substrate, right? Now we're not talking about primary substrates and methyl substrates. Those produce unstable carbocations, so the leaving group is not going to just leave. But if I have a tertiary alkyl halide like this is called tert-butyl bromide. If the leaving group just leaves, why can that happen? Why can this ionization occur? Let's think about it. You end up with what? A tertiary carbocation. And you remember that a tertiary carbocation is more stable than a secondary, more stable than a primary, and more stable than a methyl. And so that is why this can actually happen. Okay, there's nothing wrong with the leaving group just leaving. And then the ethanol then in the next step, okay, let me just draw ethanol like this. Now ethanol can either go in and attack as a nucleophile, okay, we can get a nucleophilic attack so that we do the substitution, or since you have a carbocation, yes, ethanol is not a strong base. I'd be the first guy to agree with you on that, but it's actually strong enough that it can pick up this proton and stabilize the molecule by making it neutral and causing the elimination to occur. So we're going to see both of these pathways. All right. So let's take a look. First, we're going to start with the SN1, the substitution reaction. Okay, then we'll look at the elimination after. So the substitution reaction of a tertiary substrate in an alcohol solvent like ethanol, could be methanol, could even be water, proceeds through a two-step, stepwise mechanism. Remember, if it's two steps or stepwise, that's what I was calling one at a time. First, you have the first step, then you have the second step. So step one, first step, is going to be just your loss of leaving group. The bromine just spontaneously leaves as a bromide. Again, this can occur because you end up with a stable carbocation. The second step is going to be the nucleophilic attack. And if you're looking at it and go, whoa, Mr. Dion, there's a third step. Well, yes, sometimes there is, okay? And in this case, there has to be, where the ethanol comes along and it behaves as a base and it abstracts this proton to make this, compound neutral again. So we end up with our substitution product. And so again, even though it's actually three steps, the last step is just a proton transfer. And so we actually have a name for this reaction, this kind of SN1. We call it a solvolysis reaction. Why? Because the solvent is also the nucleophile. So if you're saying, are you telling me that this reaction just occurs spontaneously if I just mix up some tert-butyl bromide and some ethanol? Okay, I mix tert-butyl bromide and ethanol, and I'm going to end up with the product? Yes, that's exactly what I'm saying, okay? So there you go, an SN1 reaction. Now, if you look at the reaction coordinate diagram here, take a look at this. It says here that the highest energy transition state in the SN1 is for the formation of the carbocation, okay? That's, so if that has the highest activation energy or the highest energy transition state, that would have to be the rate determining step, right? You guys remember the activation energy, right? It's not really drawn in the right place, but you guys remember the activation energy, this activation energy here is related to rate, right? Activation energy is proportional to rate. The higher the activation energy, the slower the rate. The lower the activation energy, the faster the rate. That's why catalyzed reactions are so fast, because they lower the activation energy. Well, you see that of this whole darn thing here. You've got a few different activation energies. You've got one for the loss of leaving group, one for the nucleophilic attack, right? There's one here, then there's one here, okay, which is really small. But the bottom line is this is the biggest one. And so what does that tell you? That one is going to determine the rate of the step, okay? Oh, sorry, the rate of the reaction. So we say that the formation of the carbocation is the rate determining step. You know, when I first started teaching this class, I mean, I obviously went through this with my students and I brought it up. You know, I mentioned loss of leaving group, the rate determining step in an SN1, okay? However, I wasn't prepared for how much this gets tested in the ACS and MCAT and DET. And so it's one of those things that now I make a point of telling my students flat out that this comes up a lot. Okay, for some reason, they love testing students on this concept. And so please remember this, okay, that when it turns out that in an SN1, the whole reaction rate is really based off of that loss of leaving group, you know, how easily or readily that occurs. Okay, so let's talk about this SN1 reaction. I've kind of gone over this already. I told you that the rate is equal to the rate constant multiplied by the concentration of the substrate. So it's a first order kinetics reaction. And so now it says it's clear that when substitution occurs via carbocation intermediate, it's called an SN1, right? How do we know that it's first order, right? I think there's a question in the textbook where it asks you, you know, like how would you actually determine that the reaction is first order? What you would do is you'd go back to a reaction like this one here, okay? And first you would change the concentration of the alkyl halide and you would see that it affects the reaction rate. Then you would go and you would change the concentration or change the, you would change the relative concentration of the ethanol. And then you'd find that it doesn't do anything to the rate. And then you'd say, well, that doesn't have an effect on the rate. So therefore the reaction only depends on the concentration of the alkyl halide. And so it's a first order reaction. If you guys remember who remembers the method of initial rates that you did where you compared different reaction rates and then you were able to determine rate is equal to K times A to the power of N times B to the power of M and stuff like that. And you did a whole bunch of problems where you would have solved for N and then you would have solved for M, okay? Well, that's the idea is the same concept here, except, you know, now we're actually talking about what the experiment would be, that you would just vary the concentration of your alkyl halide, and that would tell you that it's an SN1 reaction. Anyhow, I'm kind of rambling on here, but the bottom line is substitution, right? S, and nucleophilic, and then unimolecular. Unimolecular is just first order. First order. That's all that means. Okay. So let's take a look at the mechanism in detail. And this mechanism you need to know off by heart, right? This is just an SN1 mechanism. And if you're looking at it, go, well, I could figure this out pretty quickly, you know. It's just a loss of leaving group to form a carbocation, followed by a nucleophilic attack. Close the door. Sorry, the formation of your carbocation followed by nucleophilic attack. So just remember, if you're like, where's the proton transfer? Where's that last step? Well, that depends on your nucleophile. If your nucleophile is a neutral species, like an alcohol, yes, in that case, you would need to have a third step. But if your nucleophile is negative, like it is here, then in that case, it's just a two-step process, right? So there you go, SN1. So what about the E1? So now we've covered SN2, E2, and this morning, so far, we've covered SN1. So let's get into the E1 reaction, okay? It says here, the elimination of a tertiary substrate in an alcohol solvent, like ethanol, proceeds through the same old two-step or stepwise mechanism. Again, and I'm repeating myself here, but we're learning the subject. So 2 steps, that's what I called one at a time. The first step is going to be the loss of the leaving group, and the second step is just going to be the elimination of the beta hydrogen. You see that there's actually, you know, beta hydrogen here and here, it doesn't matter, right? But they all give you the same product in this specific case. You end up with this molecule. This is a molecule you could learn how to name. This is called isobutylene. Isobutylene. It's actually used in a polymerization reaction to make isobutyl rubber, which is used in things like basketballs. Anyhow, that's neither here nor there for this lecture. But anyhow, again, this E1 reaction follows the exact same rate law, right? It's a first order reaction. And so it would be rate is equal to K multiplied by the concentration of your alkyl halide. That is all, first order reaction. Now, it says here that the rate of the E1 reaction is the same as for the SN1. Okay, so they both have the same rate law, so the same rate. The rate determining step is going to be the formation of the carbocation intermediate for both of them. Okay, so let's highlight this. Rate determining step is the formation of the carbocation intermediate. That applies for both of them, the SN1 and the E1. You can see here that this step, the loss of the leaving group, has the highest, we'll put here highest activation energy, and therefore it's the rate determining step. Now, if you're astute, and I know that you all are really astute, I know you guys all pay close attention to all the details in organic chemistry by, the great questions that you ask. Well, I bet you're looking at these and going, well, hold on, Mr. Dion, you've got the substitution product here, but when it comes to elimination products, right, this is a di-substituted alkene, and you taught me that a mono-substituted alkene was less stable, and that a tri-substituted was more stable, and that tetra-substituted was the most stable. So usually the way it goes is if it's di or mono-substituted, it's going to be slightly less stable than the SN1 product. And if it's tri or tetra-substituted, it's going to be slightly more stable than the SN1 product. Don't worry, you're not going to be really tested on that. In any kind of detail. I'm not going to ask you which one of these, is this E1 product more stable than this SN1 product. That's kind of splitting hairs. But in case you're wondering, that's kind of the trend. It generally follows that trend. Okay. Now, what about rearrangements? Okay. Here's something. When did we discuss rearrangements? I guess we kind of learned about carbocation rearrangement. Not I guess. I know we learned about them in chapter 2. Remember that chapter about resonance, and then we talked about carbocations, and then I said one of the kind of facts of life in organic chemistry is if a carbocation rearrangement can happen, it will happen. Okay, so when you form a carbocation, right? If you go back to this example here, when you form this carbocation that I have in the blue circle, nobody asked me a question like, oh, is there going to be a rearrangement, right? Because you obviously can tell there isn't going to be any rearrangement here, but sometimes it can happen. And so that, what would I say? That increases the complexity of an SN1 or an E1 reactions, because now you got to start thinking about that, right? Right? If you were to take a look at this compound here, it's a secondary alkyl halide, okay? So that means that it's not going to be super susceptible to SN2 or E2, and you're in just water as your solvent. So you don't have a strong base or a strong nucleophile. So that tells you that the only thing that can happen would be either an SN1 or an E1 reaction. Now, they haven't even drawn the products of the E1. They said that's neither here nor there. They're trying to prove a point in the textbook, which is this. After the leaving group leaves, okay, I'll just scribble the carbocation that would result would be this here, right? Now that carbocation, if it undergoes a nucleophilic attack in a proton transfer, it's going to give you this alcohol. However, look at this blue proton. You guys know that blue proton can undergo a hydride shift, and then you would end up with this carbocation. Now, obviously, this carbocation, after it undergoes a nucleophilic attack in a proton transfer, it's going to give you this alcohol. So we end up with a mixture, and plus we also get some elimination products in this case. And so if you're wondering, do I have to be able to predict this? Yes, you have to be able to say, okay, this is an SN1 reaction. First step is going to be a loss of leaving group. I'm going to form a carbocation. Will that carbocation rearrange? If it does, then you have to take it into consideration. If it doesn't, then don't worry about it. Let's get some practice with this one here, okay? You see you get the SN1 product, then you also get a product after a rearrangement. So if we just draw the leaving group leaving, okay, I know I don't have a lot of Taylor Swift blank space down here, but anyhow, if I draw the carbocation that results after the loss of leaving group, what's going to happen? I'm going to get a nucleophilic attack, then a proton transfer, and I'm going to get this product. But you know that that secondary carbocation can undergo a methyl shift, what we call a methide shift here, to give me what? It would give you what? It would give you this, where you have the methyl group over here now, and you have this tertiary carbocation. Then after that undergoes a nucleophilic attack and a proton transfer, you end up with this product. So, right, again, you kind of have to be Johnny on the spot with recognizing, okay, yeah, I've got a loss of leaving group, but after that occurs, can I get a carbocation rearrangement? And don't stress. They don't all have some kind of carbocation rearrangement occurring, but it can happen. And so you have to be aware of that. Now, before we do some practice, so I had that practice question. Where was it? I thought I had one. But, no, we still have some more content to cover before we get into some practice. So you're going to have to bear with me for a few more minutes, okay? I know it's early on a Thursday, but I just like to see what we have coming up, okay? So let's take a look at a couple more concepts, and then we might take a short break here, okay? Just to kind of digest the content. Now, if you look at this substrate here, do you guys remember this guy? He came up last class. This is called neopentyl bromide. So somebody asked me, you know, when you're looking at the products that are formed, do you have to be able to predict which one would be more abundant? We're going to look at that in a little bit. Yeah, we'll take a look at that in a few minutes. Anyhow, so Isaac, I got an example for you here. Okay, this is kind of a specific example, right? Neopentyl bromide is a very specific compound. Okay, but this compound is a primary alkyl halide, and so you might not expect it to react in an SN1. You might say SN1. Well, why would that happen? Right? This is primary. You just told me that you know, SN1 reactions work best with a tertiary alkyl halide because it, you know, the leaving group leaves and you form a stable carbocation. Well, do you remember last lecture that this compound, it came up and it said it was virtually unreactive in an SN2 because of all the substitution you have at the beta carbon? Okay, we did talk about that last class. So check this out. This is a really strange reaction. Okay, I shouldn't say strange. It's kind of maybe interesting is a better word here. Is that, yes, this is a primary alkyl halide, but you get the leaving group leaving, and you get a methide shift occurring simultaneously in this case. So check this out, okay? It says here that a primary carbocation is too unstable to form, okay? So if I was to, and don't draw this because it's a heresy, but if you just drew a curved arrow like that and say, there you go, leaving group leaves, that could never, ever happen because you'd end up with a primary carbocation, so I'm going to delete it, which is unstable. So in this specific case, you get the leaving group happening. So this is the loss of leaving group, but you also get a rearrangement occurring simultaneously to give you a tertiary carbocation. Now, again, this is a very specific case that I think you should know. Okay, it's very, very specific, but it is in your textbook, so he does consider it to be important. So once you get your tertiary carbocation, it undergoes the nucleophilic attack and, of course, the proton transfer in the last step to give you this tertiary alcohol. So this part here, the loss of leaving group and the methide shift, that's concerted, right? What does concerted mean? Concerted just means that both curved arrows occur at the exact same time. Now, last class, when we studied SN2, we said, let's take a look at some data, you know. Now, in this one here, really the only thing I'm concerned about here is it says that SN1 and E1 reactions are faster in polar protic solvents. So let's take a look here, okay? I'm not going to worry about the nucleophile so much in this one, okay? What I'm more concerned about is this comparison. So follow along with me. It's comparing what's called a protic solvent versus an aprotic solvent, okay? So maybe I'll use a different color for that. So we use blue, okay? So protic solvent versus aprotic solvent. So it says here, faster in a protic solvent. Okay, so what does that mean exactly? If you don't remember what a protic solvent is, I can go over it with you. It's a solvent that is capable of hydrogen bonding. Okay, so if you have some kind of solvent that is capable of hydrogen bonding, like methanol, right? You can clearly see that methanol is capable of hydrogen bonding. Then the reaction is going to be faster Then in a solvent like DMF, that stands for dimethylformamide. So DMF is this. So if we draw dimethylformamide, it looks, dimethylformamide. Okay. You have a nitrogen and you have an oxygen in dimethylformamide, but neither of them are bound directly to a hydrogen, so there's no hydrogen bonding. And so the idea is this, is that SN1 reactions go faster in, or are faster in polar protic solvents. Now what they're showing here is the rate of SN2 reaction, so it's kind of like sticking something else in the middle of the slide presentation here, because this is a methyl halide. So again, this is not a chart of SN1, this is a chart of SN2 reactions. Then it just shows you that SN2 reactions go faster in an aprotic solvent. So again, so let's figure this out. SN1 and E1 reactions faster in polar protic solvents. Those are solvents capable of hydrogen bonding. SN2 reactions, okay, faster in aprotic solvents. Aprotic solvents. And an aprotic solvent is one that is incapable of hydrogen bonding. So that's really the crux of what you need to know about solvents. So it says here, what's the effect? Okay, so the effect is this, is that for an SN2 reaction, we said a polar aprotic solvent is going to be the best. Why would that be? Okay, so this is an SN2, come on. This is an SN2 mechanism shown right here, right? It's just concerted. There's just one transition state, right? Nucleophilic attack and loss of leaving group occur simultaneously. So what happens is that when you have a polar aprotic solvent, what it does is it doesn't stabilize the nucleophile, so it raises its energy and therefore it lowers the activation energy of the reaction. But for an SN1, it's pretty different, okay? It says here that polar protic solvents, what they do is they stabilize the carbocation. So that brings, so if this is your carbocation, right, I'll just put carbocation is where this blue dot is here and here. You can see how it lowers the activation energy to make that carbocation. So that's all it does. And again, I don't really test my students a ton on this. I think the most important thing for you to know is that an SN2 reaction is one step, whereas an SN1 reaction is two steps. I think that's more pertinent. So then just talking about the leaving groups. So if you remember when we first, I think the first slide that I presented in this entire chapter, I said that chloride, bromide, and iodide are good leaving groups, but fluoride is not a good leaving group. Well, the reason why is that iodine, bromine, and so iodide, bromide, and chloride are the conjugate bases of strong acids, whereas fluoride isn't. But if you take a look at chloride, bromide, and iodide, it turns out that iodide is actually the best leaving group, bromide is lower, and then chloride is the worst of the good leaving groups, right? Okay, now why would that be? If you're wondering, hey, does that mean that HI is a stronger acid than HCl? Yes, absolutely, and HBr is somewhere in the middle. But if you think about it, you know, if you go down the group of the halogens, okay, if you go down from fluorine to chlorine to bromine to iodine, remember that the size of the atom gets bigger and bigger as you go down. And so since the iodide is so big, right, it's very good at stabilizing that negative charge, whereas a chloride is quite a bit smaller and it's not nearly as good at stabilizing that negative charge. Anyhow, all right, so let's move on from there and let's talk about the stability of the substrate, because we talked about tertiary carbocations as being stable, but we also talked about, we also talked about benzylic carbocations and allylic carbocations. So follow along with me here. I'll just kind of go through the slide with you. It says, the more stable the carbocation that's formed, the faster your SN1 is going to be, right? The rate determining step is the formation of the carbocation. So the lower energy it is, the faster the reaction goes. So remember, what we call the solvolysis reaction, that was just one where your substrate reacts spontaneously in its solvent. So solvolysis for a primary and secondary alkyl halide, those don't even happen. They're just too slow because the carbocations that are formed are really unstable. So we don't get SN1 and E1 products. However, and you have to just memorize this, I guess, tertiary alkyl halides as well as benzylic and allylic halides will undergo solvolysis at some kind of reasonable rate, right? It's going to be, it says practical rate. That means we can do it in our lifetime, I guess, thanks to the stability of the carbocation. So you have to remember that not only is a tertiary carbocation really stable, a benzylic and an allylic carbocation, those are also very stable. And you might be tempted to look at these and say, wait a minute, why? This is primary, right? This is primary, right? This carbon is only attached to one carbon. This is only attached to one carbon. You're right. So what's the key? It's resonance, okay? These two are resonance stabilized, and we know, right, the two words go together, resonance stabilized. So since they're stabilized, they are also susceptible to SN1 and E1 reactions. All right, so what you've got to be able to do, is it challenging? Yes, okay? But you, as a student of organic chemistry, it says here, be able to judge, all right? Judge not, well, you can judge in organic chemistry, okay? Be able to judge whether or not an alkyl halide will undergo a solvolysis. Remember, solvolysis is just a sassy way, it's just a fancy way of saying, is it going to undergo an SN1 or an E1? That's all solvolysis means, nothing more than that, okay? In general, primary and secondary alkyl halides, SN1 and E1, it's not going to happen unless the carbocation can rearrange to something more stable at the same time as the leaving group is leaving. And so the example that we looked at for that was the neopentyl bromide. We did look at one exception there. And then tertiary and allylic benzylic, tertiary allylic and benzylic alkyl halides can undergo a solvolysis. Why? Because they form stable carbocations. So you really got to remember these three, okay? Tertiary, benzylic, and allylic. So if I give you a substrate like this, right, you can't just say, okay, well, this is secondary, you know, no SN1 and E1. Whoa, 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 whoa. This is a benzylic position, right? The carbon attached directly to the aromatic ring. That's benzylic. So if this leaving group's to leave, or this, if I draw a curved arrow where I show that leaving group leaving, that blue curved arrow is not a heresy, okay? I'm not going to get arrested for that curved arrow. Why? Because I end up with a secondary carbocation, but holy heck, man, it's secondary and benzylic. So you could draw all kinds of resonance forms for it. Give me a thumbs up if you follow me on that. The idea that benzylic and allylic are okay. They get a thumbs up for a SN1 or an E1. It's not crazy. Okay, cool. So you can see why, and this isn't directly related to the slide, but this is just kind of me talking about my philosophy about organic chemistry. But you can see why, to be a good organic chemist, and I don't consider myself to be a great observer, but you have to be observant. You know, you have to be observant, and you have to kind of notice things and look carefully at what you're doing. You know, back in the olden days when you were in general chemistry 1, you did formulas like D is equal to M over V, right? You plug the number of grams, you plug the volume in, you press equals on a calculator, and you're done. You know, I'm not saying that that doesn't require thought, but not a lot. Okay, not a ton of thought. Okay, even if you use PV equals nRT, if you understand the units, you know, you can solve for T, right? You can say PV over nR, right? Whereas here in organic chemistry, we have no calculator to help us with anything, very rarely. And so it's a lot about knowing, you know, what's going to happen here. Okay, I've got a benzylic substrate. So yes, the leaving group can leave. I'm in water. It's not a strong base. It's not a strong nucleophile. So that means SN2 and E2 are out of the question. So that means I've got to draw the products of an SN1 and an E1 reaction, right? So now, if you're wondering about regioselectivity, you guys remember Zaitsev and Hoffman? Remember with E2, we could control, oh, I have it, it's written here. With E2, we could control which isomer we got. Remember that by choosing a hindered versus an unhindered base, okay? It turns out that with E1, there's no way to really control it, okay? It says here, E1 reactions are regioselective, but we cannot control the regioselectivity like we could with an E2. With an E2, you're like, I'll pick a hindered base. That means I'm going to get the Hoffman product, right? I'll pick an unhindered base. That means I'm going to get the Zaitsev product. Well, E1 reactions, they pretty much always give you, they will always give you the most stable alkene. So if you look at these two alkenes, I mean, which one's major? This one is tri-substituted and this one is di-substituted. So this is going to be the major product of the reaction, right? So, you know, if you're wondering, will I be asked to draw all these products? Yes, okay. How do you do that? Okay, like this. You're going to look at the substrate, the alkyl halide. You're going to say to yourself, it's tertiary. Okay, so that means SN2 and E2, forget about it. They're not happening. If the leaving group leaves, I'm going to end up with a carbocation. That carbocation is going to look like this. There is no reason for that tertiary carbocation to undergo a rearrangement. So now I know that I'm going to have a nucleophilic attack followed by a proton transfer, which is going to give me the substitution product. But if I look at this carefully, I see there are two types of beta protons. There's these red type and there's these green type down here. So if I abstract the green proton, I'm going to end up with this product. And if I abstract the red proton, I'm going to end up with this product here. And the most substituted alkene in this case is going to be the major product of the E1 elimination. All right, so same idea here. If you're looking at this and going, holy smokes, am I expected to predict all these? Yes. Okay, again, it's logical. There is a logic to it. Is it easy? No, but there is a logic to it. Again, you would look at the starting material. You'd say it's a tertiary alkyl halide. SN2, E2, forget about it. I'm in water. Water is not a strong nucleophile. It is not a strong base. But if I lose the leaving group, I'm going to end up with what? I'm going to end up with this tertiary carbocation. There is no reason in this universe for this carbocation to rearrange. Okay, so I can get a nucleophilic attack and loss of leaving group, which is going to give me this alcohol. But when it comes to beta protons, I've got these types of blue protons here and these black protons here. If I abstract the blue proton, right, if I pull off the blue proton, that's going to give me this product here, the Hoffman product. However, when I abstract the black proton, I can end up with either the cis molecule or the trans molecule. And you're going to get both of these. Now, if you look at the cis and trans compounds, you see that those are both tri-substituted, so they're both in the running for being the major product. But we see that the cis product is actually the E product, and so that is the more stable of the two. This is actually a question we ask sometimes when people come in for an interview. We'll ask them, could you have a compound that is E and, come on, pen, E and cis? Is that even possible? And sometimes they'll say, oh, let me think about that. So this compound is cis, right? Because you have two methyl groups that are on the same side. So that is definitely a cis compound. There's no arguing that. So yes, this is a cis compound, but is it E? Well, if you look at the four groups, on this carbon, the ethyl is going to have a higher priority. And on this carbon, the methyl group has higher priority. And so yes, this is an E compound and it's also cis. So it is possible to have that. So what's the conclusion here for this specific reaction shown on this page? Is that it still holds true that the E1 is going to give you the most stable alkene, okay, as the major product. If there's two stereoisomers, so these two compounds are diastereomers, the one that's least sterically hindered is going to be the more stable, and so it's going to be the major product. So again, E1 reactions are stereoselective, but you cannot control the stereoselectivity. You cannot control it's stereoselective, but you end up with a mixture of everything. It's regioselective, but you can't control the regioselectivity the same way you could with an E2 reaction. Now, just a couple more thoughts before we get into some practice problems here. The alpha carbon, so once your leaving group leaves, your alpha carbon becomes sp2 hybridized, right? So the carbocation, you know, is sp2 hybridized, therefore it's trigonal planar. And so the nucleophile can come in and it can attack from either side. So you're going to get a racemic mixture. So you'll get a racemic mixture. But it turns out that you actually don't get a 50-50 mixture of these two. Okay. And this is just, I'm going to put here, will not ask on quiz. Okay, I'm not going to ask you this on a quiz. It could be on a homework, because the homework, you can always go back and refer to this, your notes and stuff. But instead of getting completely a racemic mixture, usually you get a little bit more of the inversion of configuration product and a little less of the retention. And the reason why is because when the leaving group is actually leaving, so here's my leaving group leaving, it's hard for the nucleophile to get in there, right? It doesn't want to attack on that side. So just based off of the rate of the reaction, you get a little less of the retention of configuration. You mostly get backside attack. But again, I'm not going to ask you that on a quiz, so don't stress about that a whole lot. What I would like to stress about, and I don't mean stress about, what I would like to look at are these two reactions here.